Okay, let's start with the Fourier transform. So give a signal in time domain. When you integrate it, you will get integrate it and times the e to the minus I omega t. You will get the signal in frequency spectrum. If you are given a frequency spectrum signal times e to the I omega t and integrate it, and then you divide it by 1/2 pi, you will get the signal in time domain. Fourier transform pairs, so it's a pair. And this is the notation. Example, so if you are given a exponential decay function, plot the amplitude spectrum for f omega. Okay, so we want to Fourier transform it. Then I change the limit to 0 because it only starts from 0. Otherwise, it's just 0 the value. So because ut is a Heaviside step function, so you just let it be 1 there. So you have e to the minus bt times e to the minus omega t, then you add it up and integrate it, then you divide it to the denominator, then you fill in the values, can get that. And when you plot it on the omega x-axis as x-axis, it will look like this. Okay, so it says there are two spectrum, frequency spectrum and amplitude spectrum, where it has the amplitude or modulus sign there. Next, determine the Fourier transform of a top hat. So this is just one when t equals minus a divided by 2 and a divided by 2. The Fourier transform will be because it is 1 there, so you change the limit to express this is a top hat. So this is just 1 there. And then you do the integration. So you will have I omega on the bottom and 1 on the top. And you have a minus sign. And e. And you sub in the values minus omega a divided by 2 minus, add a bracket, e to the I omega a divided by 2, because minus gets plus. And you remember this one is the sign, the Euler function. So you will be left with 2, because the Euler function equals 1 to I e minus I omega minus e to the I omega. Okay. Then we have a trend of top hats, so it's repeating itself. Sine series with this on-off ratio is basically this divided by that. If A is made smaller, so these are smaller, then it will be sampled closely. The sinc function. The Fourier transform of a top hat is a sinc function. This will need to be remembered. It doesn't look like sinc function at first, but you rearrange it. You want to get a omega a divided by 2 on the bottom. So you will times an a at first in the front. So you will get a sinc function. Sinc function has 2 definitions. We will usually use this one. This is our note from the formula booklet. Example 3 will use a triangle function. Triangle function where we have 1 plus t divided by a here and 1 minus t divided by a there. So you need to remember this 1 plus t divided by a and 1 minus t divided by a. The Fourier transform will be, so you will divide it into two parts from minus a to 0 and 0 to a. So for this part, you just put in 1 plus t divided by a, and similar for the next part. Then, so how come it becomes a? You change the limit because you first swap these two signs becomes this equation. Then you want to change the limit. So the t will be minus t. So it will become a plus sign, and you add them together, you will get this function. Check that integral. So to integrate it, you need to use integrate by parts, where you have u is this one, dv by dt is cos, and 1 minus 1 over a and v. I don't know if we will be using this one in our exam, but better to bookmark it. Some properties, there are 7 or 8 properties in total. First property is linearity property. So you want to Fourier transform ft and gt, you add a coefficient times a coefficient in front of each equation, then you get a Fourier transform with respective coefficient in front of it. So you just can take the coefficient out of the integral. Dual property, if you want to Fourier transform a ft, becomes a capital F omega. If you want to Fourier transform a capital Ft, then you get a 2 pi f minus omega. You need to remember this clearly. So better to memorize it. Ft times Ft will become a 2 pi f minus omega. How to prove this? We will start from the inverse Fourier transform, where t and omega are just symbols, so we can replace it. Replace t with minus omega and omega with t. And it does not flip the limits of integration. So put in f minus omega. Then you will get, so you will get replace omega by, okay, you replace omega by t and replace t by minus omega. So you will get this expression. This expression, so it looks like you are Fourier transform the ft, but you divide it by 2 pi. So you will say you are Fourier transform ft. Note this is not an inverse Fourier transform because we have a minus sign here. So you multiply it to the left. So the right, you just left with a Fourier transform of ft. And on the left, because you multiply by 2 pi, it will become 2 pi f minus omega. Property 2, we just talk about this one and come to the property 3, parameter scaling and similarity property. So okay, so you will have a parameter s there, and you Fourier transform it, it will come to the bottom as well as the omega s. So we need to consider for both s greater than 0 and minus 0 circumstance. So first, you Fourier transform f as t, so you put it in as usual. Then you let p equals st. If you let p equals st, then it will give, so t will become p minus s. So this will become omega p minus divided by s, sorry. So it will look like fp e minus omega p by si. And you will have omega divided by s for its inside the bracket. Because normally you have ft e to the minus omega t, right? And now you have a extra s here, so you have to put this into the bracket. To prove it, if you have st, then it will come to the denominator. So this is when s is smaller than 0. Similar thing happening here. And because the minus sign, we swap the integral, the limit. And finally, you will get this expression after flipping around the limit. Why it has a minus sign, minus limit infinity on the top? Because we let p equals minus st. Because s is minus 0, so modulus is still positive 1, but you add another minus sign, so p will become negative. So this is thing that needs to be remembered. The property 3, the Fourier transform of ft. Fourier transform of gt equals Fourier transform of sft. So this is illustrating a wrong case where s equals a divided by b. So when it gets broader, s must be smaller than 1. So s is always on the denominator and omega divided by s from our previous proof. Find the Fourier transform of ft equals 1 over t times sine t. The Fourier transform pair of a unit pulse of a half with 1 over 2. Half with unit pulse, so this is a top hat. Use a 1 over t here. It will be transformed into, so this is a sinc function, sine omega by t divided by omega by 2. So okay, then we want to, now we have, okay, replace the omega by t. Okay, so this is the dual property. So you will get a 2 pi over there. So this is a ft, capital Ft. And this is the f minus omega. They want to use the parameter scaling. So s equals 2. You divide by 2 there, then you will get this expression. General point a note about scaling. The narrower the function in time, the broader is its frequency spectrum. Parameter shifting. So in time domain minus a, then you will introduce a e to the minus omega a in the frequency spectrum. To illustrate, to prove it, you will put a ft minus a into the transform expression. Then you replace by p. Then you will get so e will become e to the minus omega p plus a. So you split it, you will get e minus I omega a in the front because it is not involved in dp, the integration. So you will finally come to this expression. What if f t plus a? It will do the same. So first you will have f t plus a e to the minus omega t dt. Replace t, p equals t plus a. So t will become p minus a. Then you will have integrate fp e minus I omega t I omega p times e to the I omega a and dp. Then you will put this out, will give you e I omega a f omega. So this is when you have a plus sign there. Next, find the Fourier transform of ft. Fourier transform of a top hat is a sinc function, and the version time shifted to the left. To the left involves t plus a divided by 2, yes. Yeah, I just proved it. Shifted to the right, it's plus sign. So you will add a plus sign here. And this expression is just a Fourier transform of the top hat. Subtract the right shifted. Okay, so now you will get a graph look like this. So you just subtract those two, delay to the left and to the right equations, and scale the amplitude by 2. You will get a formula like this.